All right, we've got 3 days in a row. We've even got a refactor video for day 3. So let's take a look at day 4. The gondola takes us up. Strangely though, the ground doesn't seem to be coming with you. Why would the ground come with us on a gondola? As we exit, the air is warmer. It's also humid. There's an elf on the floor playing a game. How may be of service? This is Island. I bet the gardener would know. Sorry, Mario, your princess is in a different castle. Our elves are on a different island. The small kind surrounded by water, not the floating kind. Trying to borrow their boat. Scratch cards. 2 lists of numbers separated by a vertical bar, a list of winning numbers, and then a list of numbers you have. Here's our input. As far as the elf has been able to figure out, you have to figure out which of the numbers you have appear in the list of winning numbers. The first match makes the card worth 1 point, and each match after the first doubles the point value of that card. So card 1 has 5 winning numbers, 41, 48, 83, 86, and 17. So that's these on the left. And 8 numbers you have, 83, 86, 6, 53 here, so that's on the right. Of the numbers you have, 4 of them are winning numbers. That means card 1 is worth 8 points. 1 for the first match, and then doubled 3 times for each of the matches after the first. I think that's 2 to the third, right? 2 times 2 times 2. So this is going to be a power operation for us. Yada yada. In this example, the elf's pile of scratch cards worth 13 points. Take a seat in a large pile of colorful cards. How many points are they worth in total? Okay, so we've got this. This actually seems pretty reasonable, unless there's some trick, which, you know, there always could be in part 2. Just day 4. Just create day 4. I knew it looked weird for some reason. So day 4, source, part 1, throw our test in. Somebody mentioned in doc, which I think is this, which I have never heard of before. So in doc takes a multi-line string and unindents it at compile time. So that's kind of cool. It's a little bit annoying to have a third-party dependency to do this, I think. But I actually ran into an issue where I lost half an hour to having some space here. So I just wanted to call out in doc and that it exists, and if you want to use it, you can. So here's our cards. This is going to be a hash set on the left, I think. It's a hash set one way or the other. We either loop over our numbers and check to see if they're in the winning numbers, or we loop over their numbers and check to see if any of those are numbers we have. I think for us, it won't matter which one we do. So let's say that the card is going to be a hash set. Actually, I think both of these can be hash sets, now that I think about it. The only downside to that would be if we have double numbers anywhere. I don't see doubles anywhere in here. Let's check the input just as a sanity check. Scan wise, I don't see anything where it's like 6 and then another 6. So I think a hash set will work. We can definitely verify that though, before we continue, or not before we continue, but so the elves are worth 13 points. And my thought processes here is that we can hash set the left, hash set the right, and then do the intersection. And based on the intersection length, we'll know what power number to use. And then we do 2 to that power, and we add those up and we're done. So as I like to do, I am going to end up with a non-parser here. That's going to take each of these cards and return us one of these cards. And they're going to have the, I guess we'll call this winning numbers hash set and my numbers, just so I keep this straight in my head, which one is winning and which one is mine, because I already see this is going to be the same kind of issue as like keeping X and Y in day 3. I'm not going to remember which side is the one that we needed to work with. So I'm going to make this a struct. I derived a debug on it because I always do, so that we can use the debug macro. This is just going to be called card. I guess it should be called cards and we should do them all, but this will be a vec of card then. And this will be a separated list 1, but first we need to discard preceded tag card space. Or I guess we'll do delimited here. Digit 1 tag colon space, right? And then instead of preceded, we'll do delimited. We of course need to import everything. One of the things I wish NOM had was a prelude in general, but it doesn't, and that's fine. So separated list 1, I guess this is separated pair, right? And I'll just call this set tag pipe with 2 spaces. Set, and it takes the input. So this set parser is going to be a hash set of I32s. And this is super easy for us because this is just a separated list 1 separated by space. Although now that I'm noticing, there's multiple variations of space here. So I think what we do here instead is space 1 for the separator and digit 1. But instead of digit 1, I think what we can do is complete I32, space 1, separated list 1, getting all of our stuff together. I don't have our tests. I need to update iTerm. I don't have our tests running. So let's do day 4, part 1 over here. And this will give us the type errors for these squiggles, which are probably just, I guess we could do fold many one here too. I was just thinking we're going to build up a structure no matter what. This is the docs for fold many 0, but it will be the exact same. So we're going to have our parser, and then we're going to construct the thing. So there's two things that we need to do. One is to get this into here, and this is not going to be a vec new. This is going to be a hash set new, and this is not going to be a vec. This is going to be a hash set, and there's going to be the item, and it's going to be a push. I think it's insert, actually. Yeah, it's going to be insert. And of course, we need to import that, complete I32. The only thing that we need to deal with is that white space. And we've got a couple of things here. We've got preceded, terminated, and whatnot, as well as tuple. So I think what we're going to do here is this is going to be preceded, complete I32. Goes that way, right? First and second. Yeah. I want terminated. I don't want preceded. Whoops. And then this is going to be space 1. It could be space 0. I think I'll make it space 0 instead. So this should work. Fold many 1, terminated. We pull I32s separated by white space. We build a hash set out of those things, and that gives us a set. This separated pair doesn't give us a card. So if I'm correct, this should give us 2 sets, A and B, right? Which should be our winning numbers and my numbers. And we build our card, and we didn't import the parser trait. So .map in this case is a trait on parser, or a function on the parser trait from nom. So separated pair here is a parser. The type signature is a little bit complicated, so I'm not going to show it to you. But separated pair is a parser. The parser trait needs to be in scope if we are going to use the parser function map. And if we do this, we need to call .parse because of a slight iffiness. So in Nightly, there's something called call syntax, or that's not what it's called, but that, like, building something up so that you can call it like it's a function is a feature of Nightly Rust. We are not currently using Nightly Rust, so we are going to use this .parse function. This, of course, is on the wrong parser. Is it on the wrong parser? No, that's separated pair. We're good. This is going to be a vec of cards. So this needs to be, we're just going to pull this out into its own. And then here we do a separated list, line ending, card, input. This is going to be separated list 1 because we have to have at least one. Line ending needs to come in to scope. And then we find out why my hash sets are red squigglies. Expected hash set U32 found I32. Did I mess something up here? Oh, I made these U32s. Whoops. That's fine. We can totally do U32s. So now we have cards. So now what we have is hash sets of U32s parsed out like this. We have the card data. This is a vec of cards. I am going to impl card here and define a function called score, which takes self and returns. What are we supposed to be returning here? 2 to the power of the matches. So we'll do a U32. So if we do self.winning numbers, we do intersection self.myNumbers, we should get another hash set, and this will be power, right? Let's get rid of the type inlays here. Self.myNumbers needs to be a reference. So self, winning numbers, intersection, my numbers, count. That's the power. And then 2.pow power, I believe, is the right function. I don't expected U32 found U size. That's totally fine. We can as U32 this because we're never going to have a number that big. Looks like one of the PRs to the just file had an issue, so we'll fix that some other time. So this should give us the score now, and then we do card data .iter .map card.score .sum U32. We'll call this result. This will be okay result to string. We're not using input here, so I'm going to put an underscore there, which is a feature of Rust. So now the Rust compiler knows we aren't trying to use this. Okay, we've got our test failure here. It's a tag issue. Is the tag because of the pipe? Yes, the tag is because of the pipe because I included the white space at the end. The left 13, right 16. So let's get that running. Oh, did I write something the wrong way? Just test. Yeah, this is -s. So our tests are just running now. Let's see, map, card, whatever. Let's debug card score, because I think we have the list of those, right? Card score is 16. We're supposed to get 13, right? Card 5 has no winning wonders, so it is worth no points. So I think that might be our issue. Let's take a page out of day 1's book here and be sure. Where's part 1? And I'm going to bring this RS test in, and I'm going to dump that right here. 1, 2, 3, 4, 5, 6. We'll have 6 of them, yada, yada. So hash, case, open, close, sum answer. Cool. Get rid of all of these because we don't need them. This is line test. That's fine. Line is a string. Expected U32. That works. We're going to parse one card here. So it should be a valid card. We have stir card like that. We'll do assert equals input and an empty string because it should be an empty string at this point. We should have parsed all of the input. And then we'll say expected not equal to process line. We'll check each card score. So all of these are failing because they are all wrong, which is good for us. That looks weird. Let's get these numbers first though. So 822100. 822100. Okay. I think these are all parser failures right now. So nom error input card 6. This needs to go in card. And I believe, so now we're at write 20. I believe we have an issue with our power here. So in score, if count is 0, we don't want to run power. So what is the deal here? If there are 2 winning numbers, it is 2 to the 1. If there are 4 winning numbers, it's 2 to the 3. So I think this is something that we need. So if there is no count, then we return 0. Otherwise, it's power -1. Case 3 is failing. Interesting. What is case 3? Case 3 isn't parsing correctly. Why is case 3 not parsing correctly? Oh, because there's an extra space. I need to start using white space in these parsers instead of specific space. So if we look at the cards here, so card 1, right? Space, but card 3 is space, space. So any space between any of the card numbers needs to go away. So for this is not guaranteed either. So this is going to be space 1, and we'll make this tuple because that'll get thrown away anyway, which means we need to put our parsers into a tuple here. Cool. That value gets thrown away. This is the tag for the space after the card. So we'll do tuple here too, because this will also get thrown away. And this will also be space 1. So there has to be at least one space here. And this also needs to be wrapped in a tuple. And that should be our parsing issues gone. It is really nice how sort of maintainable and modifiable non-parsers are. I don't do a lot of like testing of the interiors here, but all of this could be split out into specific test cases and guaranteed sort of like if we change the parser in the future, we know how it would change. Okay, so our tests are all passing. We didn't get our input yet, so let's do that. A lot of input. I just dumped that into the wrong file. Whoops. Let's go down to day 4 and go to the input and save it. And we'll run this backtrace digit. Let's see, card 201. It is failing. There's a lot of space between the card and the 8 there. Is that accurate? Oh, yes, because all of this beginning space needs to be... Okay, we're just going to change all of the white space to be variable. So this is going to be space 1 for card. I don't think we actually have any left. But yeah, basically all of the white space is 24,542. Sick. So part 1, done. We'll click continue to part 2. And as usual, we'll come back to this afterwards and do a deeper dive into what's going on here. But basically, we parsed everything, we used hash sets, and we scored them and we summed them up using the intersection. So again, a win for putting our data into the right container. Let's run that to make sure, yep, all the debug logs are gone. Let's get this in here. Okay, part 2. We're about to report our findings. The rules have actually been printed on the back. There's no such thing as points. Is this whose line is it anyway? There's no such thing as points. Scratch cards only cause you to win more scratch cards equal to the number of winning numbers you have. Specifically, you win copies of the scratch cards below the winning card equal to the number of matches. So if card 10 were to have 5 matching numbers, you would win 1 copy of each of cards 11, 12, 13, 14, and 15. Copies of scratch cards are scored like normal scratch cards, and you have the same card number as the card they copied. So if you win a copy of card 10 and it has 5 matching numbers, it would then win a copy of the same cards that the original card 10 won, 11, 12, 13, 14, and 15. This process repeats until none of the copies cause you to win any more cards. Cards will never make you copy a card past the end of the table. This time, the example goes differently. Yeah, okay. Card 1 has 4 matching numbers. So that means 2, 3, 4, and 5, right? So 2, 3, 4, and 5. Yep. Original card 2 has 2 matching numbers. So you win 1 copy of each of cards 3 and 4, and so on and so forth. It looks like we're only going from top to bottom. We never go backwards, which is wonderful. That makes me think we can just calculate everything once and then sum everything up specially. So this is going to be a 2-pass. How many total scratch cards did you end up with? Oh, we don't even need to know what the values are. Okay, we only need to know the values because that influences how many we have. Okay, so 30 here, that's what this is. Our score function stays the same, right? We keep the same score. So I think what we do here is we score them all to start with. We don't sum them immediately. Let's get a test running here day 4, part 2. So if we have all the card data, right, and we can do all the scores, we probably need to collect that into a vec. And because everything else is so well typed, I can just say I'm collecting this into a vec and then use underscore to let the Rust compiler to fill this in. So result is no longer result. Result is now data, we'll say. And then we need to data.iter. And my question is, how does the multiplication of these happen? Because it's kind of recursive-ish. So let's do a fold where we keep the bank, maybe. Copies are scored like normal scratch cards. So card 1 has 4 matching numbers, which means we get an extra copy of 2, 3, 4, 5. 2 also wins a copy of 3 and 4. So we have 4 instances of card 3 because we had 2 of card 2. And that caused us to each win 1 copy of card 3. So we need to do the math each time based on the number that we have. So if we iter over this, right, our initial state is going to be something, and then we'll have the card score, right? And then the card score needs to have the ID so that we know where we are. I'm going to put unit there for now. I'm going to do this down here. We're going to enumerate so that we have the index of the card. And then we need to keep the hash map of index to number of cards that we have. So everything starts with 1. I think we can construct that from 0 to card data, that length, map over that, we get the index, and we want the index with the number 1 to start with. And we collect that into a B tree map where the key value is what, a U size here, and the value is, call it a U32. It doesn't really matter. We do need to bring in B tree map. So what we're doing here is we're taking the indices of all of the cards, right? Because I believe everything is sequentially ordered, even though, technically it doesn't have to be, right? All of these are sequentially ordered and numbered for the line number that they're on. So we actually don't need to keep the card IDs. The card IDs are just indices. So we'll keep those implicit. We have the B tree map, which is indexed to the number of cards that we have. All of those need to start with 1. This is going to be store. Store is going to sit here. We will update store as we move forward. Do we need anything else in store? I think we just need the number of cards, right? So everything starts off with 1. And then when we're done down here, what we do is store, or I guess result of this, right? So this is going to be our .values.sum. And this will be result. Then we can uncomment our stuff down here. And that leaves us with just this fold, which we need to return accumulator all the time from. And then we have the card score and the index. So for what? Index dot index plus card score, right? If we have 4 and we're at 0. So let's say card score is 4, right? That's the first card that we get. And our index is 0, or the card ID 1, Then we need to go from index plus 1 to index plus card score. We'll keep the plus 1 in here. We could do an inclusive range. This could have been ... equals, but I think it makes more sense to say index plus 1 plus card score, because then we end up at 1, 2, 3, 4. So then we can do our entry API, which should always exist, and modify value plus equals 1. This is going to have to be dereferenced, right? Accumulator needs to be mutable because we are changing things in it. And then, is that our test passing? No, our test is not passing. Okay, so we got 30 and 16. So the one thing we aren't doing is taking the number from the store for the current index and multiplying it by that. So this is value plus equals 1 only for the first card. And then let's say card number 2 has 2, right? So it's plus 1 twice. So it's plus the accumulator entry index, which has to exist, right? Actually, entry is the wrong thing here. We'll just get, and then we need a reference to get, and value is a mutable reference to a U32. So we can get away with this. So right now what we have is a mutable B tree map that we are getting access to, right? We're getting exclusive access to this so that we can modify it. This value represents something in that B tree map that we are trying to mutate. And then I'm also, while I'm holding that exclusive reference, trying to also hold a shared reference. So if we move this out to above and we dereference it, which will copy it, then we are no longer taking a reference into the accumulator. We're no longer taking a reference into that B tree map to get this value that we're adding. We've effectively cloned this value. And now our exclusive reference has exclusive access. So here on the left, we've got 30 and 31. We are doing one too many. So if I debug map here, Oh, fold is consuming, so it produced one value, which means that we have a B tree map here, which would be weird if we were going to inspect because it's not an iterator. So I could wrap our debug across this entire thing, which is a little bit weird, but it'll work out just fine. So we've got 1, 2, 4, 8, 14, and 2. So 1, which means we've got 2 of card 2, right? Oh, there we go. I was going to have to do that math in my head. 1, 2, 4, 8, 14, and 1. So card number 5 is supposed to have 1. Oh, card 5 is 14, and card 6. Right, this is plus 1. 1, 2, 4, 8, 14. 1, 2, 4, 8, 14, and 1 instance of 6. Why do I have 2 instances of 6? Is that because when we get this last, even though there was nothing for 5 additionally, we are still adding it here because we have an entry? So how do we prevent that from happening? We could start everything off at 0 and then have the value be 1 plus 2 add, and that gives us slightly off numbers for everything. So I don't like it. Do we need to special case 1? That would be weird. I don't love that, but everything else is correct. Let's do this. Print line, index I to add for everything. So index I to add, index I to add. Why does this get up to 8? There is no 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I printed this out in plain English here. I did print line, card whatever, add something to card whatever. These are 0 indexed for us, 1 indexed for the card numbers. So this should be overall a good move. Let's get some white space in here. So card 1 adds 1 to 2, 3, 4, 5, 6, 7, 8, 9. That doesn't make any sense. We're using the wrong number, that means. Card 1 has 4 matching numbers, so you win 1 copy each of the next 4 cards. Ah, that's the problem. We're doing score here, right? And it's not score that we need. It's matches. So it's not the power calculation. It's literally just the count. So we're doing score where? Here? No. Where did we? Here. And now everything passes. Okay, I was using the wrong number. I thought we were using the score. We should have been using the number of matches. Interesting note, we can now implement this in terms of matches. So score can now be self.matches. So you can do this kind of thing where you impl card and then we have self.score here and self.matches. Self.matches does some calculation that score needs, but we also need to expose. So we can access this on card, but we can also use that in score to do some calculation. Okay, let's get rid of these print lines. Get rid of this debug. So far, so good. Run part 2 then. Get this number and get our gold star. Sick. So let's take a look at how this stacks up. According to Javon, we are running in about 300 microseconds for both. About the same for Criterion, 324 and 366. We can pull this report in. We're in day 4, part 1. This is our probability distribution. Looks like we had a couple of runs that were kind of out there, like 900, 600. And this is our iterations graph. Part 2 looks pretty similar, honestly. Not too interesting today on the Criterion graphs. Our DAT profile is about 150,000 bytes or 150 kilobytes. And the flame graph I don't think is going to be very interesting here because we're not running more than a single function. So again, we approached this problem. We built a struct that represents what we needed. We built a parser to take our input and put it into the struct. This input today was particularly simple looking. But one of the really nice things is that when we write a parser like this, when we discover that there just needs to be arbitrary white space, that's something we can just drop in. We don't need to worry about it, which means that the parser is probably a little bit messier than it needs to be, but I'm okay with that for now. The most interesting part is the set parser. So fold many, terminated U32 and space 0. So this means that we are effectively doing many iterations of this parser here. So we've got a U32 that is terminated by a space, an optional space really, so it's space 0. We start off by constructing our brand new 0 hash set, and then every time we parse something out with U32, which is this item, we insert that into the hash set, and that's how we get a hash set out of this parser, using nom, living inside of our other parsers, which is really nice because we get to do custom things that return custom structs, custom data structures, and we can just bundle that up into a reusable combinator. We also did score here. We did that as an impl on card because it felt correct to me. It felt correct because we require the card to actually be able to calculate this. So if we already have a card, then we should just be able to get the score from that card. We had the useful insight that the way the scoring was working was literally 2 to the power of the count of the cards, or the count of the winning numbers, or the intersection anyway, -1. And we used hash sets to our advantage here. We didn't have to write some logic to do comparison for each side. We only had to take the hash set here, do the intersection with the other hash set. We've looked at hash set before, but hash set is basically a hash map where the values are all unit. And there's a bunch of functions here on the left. So we could do difference, contains, and the one that we used was intersection. So we do hash set number 1, hash set number 2, a.intersection, and that gives us all of the items that are in both. So in this case, it would be 2, 3. And iterator is where we get count from. So when we do this count, we do intersection, which gives us an iterator, and then we use .count. Now that gives us a U size. We know that our numbers aren't really going to go that high, so I'm okay casting here as U32. In other cases, it may make more sense to use different ways of doing that. Now, if we are at power 0, because we're trying to, return a U32, we can't do power -1 here. So we have two options, actually. We can do checked sub here, which is self minus the number that we give it, and then an option. So in that case, we would do power.checked sub 1, and we can match on this, right? And if we fill match arms here, we either have a number that we're going to do something with, in which case we do 2u32.pow num, right? Or we return 0. So now we're doing this checked subtraction. We're being like, hey, very aware that we can't go below 0. If we do go below 0, then we need to return 0 here. Otherwise, we return the power. And our test should still pass for that. Run our part 1 test here. Yep, all of our tests pass. We're good to go. Checked sub for the win. And then once we can get those scores, we can do the card data from the parser. We iterate over the card data from the parser. We map the card score, and then we sum it. And that's it. Our process function is very simple. This would be one line if I didn't have special formatting to make it easy to show on stream. And then in part 2, we switch things up a little bit. Not too bad. A lot of extra added white space into this parser. I'm actually going to take that checked sub that we just wrote and make sure I use that in part 2 here as well. Power self.matches. So all together, we could do something like self.matches.checked sub 1 and just make that effectively a one-liner. Kind of cool. We don't actually use the score here, so it doesn't really matter. We could just delete this function. But our process is quite a bit more complicated than our other process. It's not really inherently complicated here, but it does do a little bit more than our other one did, which was just summing. So again, we get our cards from our parser, we get that card data. That card data is a vec. We iterate over it. We get the number of matches. This should probably be num matches instead, right? Let's make that change. This is now num matches, which returns the number of matches. Collect that into a vec. We let Rust sort of like infer what's supposed to be inside of this vec. And if we look at the type inlays, we can see that that's a U size, but it doesn't really matter to us. So we let Rust do it. Didn't feel like typing it. We then have to do this like forward pseudo recursive kind of thing. So what we do here is we bootstrap our data. So every card, we have at least one of them. We know we have at least one of them because we have the cards in the first place, right? So we take all the indexes for all the cards. These could be card IDs. I chose to not use card IDs. I chose to 0 index them instead of 1 index like the cards are. Map over them. Again, creating this tuple that we've used before. This is going to be the key of our B-tree map. This is going to be the value. We collect into that B-tree map, and now we have a B-tree map where we have one of every card. Once we have one of every card, we can iterate over our card data, and we're going to use a fold to take that store and keep it up to date with this data that we're moving forward. We use enumerate to get the index of each card. We take the index of each card and the score for that card, and we spread that number forward using a range. So not the current card, but the next card, and the next card plus the card score as a range. So if we're at card 0 and we need to go 4 for a card score of 4, we want cards 1, 2, 3, and 4, right? Given those cards, we have to get the value of the current card. Now, this could come out, right? This doesn't need to be in here. This could be out here. We don't need to do this in every for loop. So we get the number of the current card. So if we have 2 cards of card like 95, right? And card 95 needs to spread its value over the next 3 cards. Each of those next 3 cards needs to get 2 more cards because we had 2 of 95. So we get that to add from our store, and we make sure that those other cards, 96, 97, 98, are all updated appropriately with that number. We do that using the entry API. The entry API is absolutely wonderful. And that's basically it. We take that B-tree map, we get all the values, which is the counts of all the cards, and we sum them. So not too bad today. That was about it. Let's take a look at the leaderboard and see how many people have been completing every day. So far, DeFellow looking for an internship, and new in the top 3 is Rohan. So congratulations to everybody at the top of the leaderboard. And about an hour after, we've got a whole bunch of people doing day 4 already. So we've got 45 people who have attempted or completed day 4 for both parts, which is wonderful. Love that. So that's it for today. We're getting a little bit more of the image. If you have any questions, as usual, drop them in the comments, and I will see you tomorrow for another one. Have a great rest of your night.